All right, hello. Welcome back to another Guns meeting. Today we will continue 2011 Nationals, and we are currently on number 6 on target. If A and B are non-zero unequal real numbers, and A minus B over A equals B over A minus B, what is the sum of all possible values for A over B? Well, um, what we can do is we can cross multiply on the fractions to cancel them out. That's likely going to give us a better expression to work with than what we have right now. What we have right now, we can't really analyze anything about A over B. So if we cross multiply, we'll have A minus B squared is equal to AB. This isn't really too helpful on seeing anything for A over B, so we can try expanding the left side. So then we have A squared minus 2AB plus B squared equals AB. And then we can also try moving the AB over to the side, and then we just have A squared minus 3AB plus B squared equals 0. So this is kind of like one thing that you have to notice. I don't know, it's just like a trick to notice, I guess, and that is if you divide this whole expression by B squared, then you can get an expression that is just quadratic in A over B. So if we divide this expression by B squared, you can see that we're going to get A squared over B squared minus 3A. So 1B from the B squared is going to cancel with this B. So then we'll have 1B on the bottom, and then B squared is going to cancel with B squared just like 1. And 0 over B squared is still 0. Given that B is non-zero, which it is. And then you can see that this is just going to be a quadratic function in A over B, right? So A over B squared minus 3 A over B plus 1 equals 0. So, now that we have a quadratic function with A over B, obviously we get a lot more information, right? And now it's telling us that, what we need to know what the sum of all possible values for A over B is. And, if we have the quadratic function for it, we can just find the sum of all possible values of this A over B, which is like our X with just Vieta's formulas, right? Which is just saying that the second coefficient over the first coefficient, the negative of that will be the sum of the roots of this quadratic. And the sum of the roots of this quadratic will just be the sum of the possible values of A over B. So then what we're just going to do is we're going to do negative 3 over 1. We're going to take the negative of that. And then this is just going to equal 3. Okay, and yeah, you can see that is our answer. So we probably said this before a lot, but Vieta's formulas are a good thing to know for like competition math if you don't already know them. So you should go look at them. They're probably in AOPS Volume 1 or Volume 2 somewhere, but you can also like search it up. If you don't know Vieta's, you can also just put in the quadratic formula here and find what A over B is and then sum it up, and then you can cancel out the plus or minus term. But obviously it's going to be a little bit slower than Vieta's. So again, if you don't know Vieta's, you should go search it up and try to learn about it. Okay, anything you want to say for that one, Bill?
Yeah, this is mostly just Vieta's. I don't really have anything to say, so.
Okay. The four faces of a fair tetrahedral die are numbered 1, 2, 3, and 4. Each time the die is rolled, 3 numbers are visible. If the die is rolled 3 times, what is the probability that the sum of the 9 numbers showing is 21? Express your answer as a common fraction. Okay, so we have a four-sided die. We're gonna roll it 3 times, and we want to find the probability that the sum of like 3 numbers are going to be facing up, right? It's going to land on one side, and 3 numbers are going to face up. And we want the 3 numbers from all 3 rolls, which is 9 numbers. We want to find the probability that that sum is 21. Now, so rolling 3 numbers, I don't know, it's kind of weird to analyze. For whenever you roll a set of 3 numbers that are facing up, you can just think of it you're rolling 1 number facing down. And another way you can think about the sum of your rolls is that you're summing all the faces of the of the um of the die, but the face that you roll on, the face that is covered, you're going to subtract that from your total sum, right? So it's like I can think of my sum as initially 10 because the sum of all the numbers is 10, and then I'm going to roll it, and then whatever face is on the ground is what the um is what the die stands on. Whatever that number is, I'm going to subtract it from my sum, right? So then, if I roll it on the face of 2, then it's like then I have my sum would be 10 minus 2 is 8. Um, and then so if we thought of all 3 dice rolls like this, then it would be like we have an initial sum of 3 times 10 or 30. And then we're going to subtract each of what our die rolls are, and we're just going to land it on one face. And then it says that we have to have that equaling 21, right? So like let's say my die rolls are x, y, and z, right? So then I can make an equation for it saying that 30 minus x minus y minus z is 21. Or I can move 30 over to it and negate all of this, and I would get x plus y plus z is 9. So basically, we've converted this problem to now being that the face that you roll on the ground, the sum of those three, the sum of your 3 rolls of that has to be 9, or we're finding the probability of that. And I don't know, this is slightly easier to work with than looking at 3 numbers at a time and finding that the sum is 21. So this is just like we're converting the problem into an easier problem to work with. So you might be asking like, how would I find this? How would I know how to convert this harder problem into an easier problem? Well, like the hard part of this problem is working with like the 3 numbers at a time. And so you kind of have to notice that like instead of looking at the dice as I'm rolling 3 numbers at a time, I can also look at it as I'm not rolling 1 number at a time. And then with the not rolling 1 number at a time, then you can think of the sum as you're adding up all the faces, but you're going to subtract this face that you did not roll. And then you can convert the problem into an easier problem. So now it's just like we're rolling one face out of 4 faces, and we want to find, we want to get that the sum is equal to 9, and we want to find the probability of them. And each of these rolls can be 1, 2, 3, or 4, and all of those are equal probability. So then, how are we going to do this? Well, we have 3 rolls, and 9 is a very small number. So easy and fast way we can do this is just to list down the possible combinations that we can have, or the possible combinations of die rolls that we can have to equal our sum of 9, and then finding how many ways those combinations can be arranged into permutations, and then finding the total number of ways we can roll our dice to have a sum of 9, and then put that over the total number of ways we can roll our dice, I guess. So let's first find the combinations we can have. Well, one combination will be 3, 3, 3. All threes will add up to 9. Another one will be 1, 4, 4. 1, 4, 4 will add up to 9. Another one will be 2, 3, and 4. This will add up to 9. And so this will actually be all of our combinations that we can have to have our thing to sum to 9. You can think about it a little bit more if you don't immediately see that, but yeah, this is all of our combinations. So now you want to see how many times can each of these permutations, or sorry, these combinations can be permuted, and that will give us, that many cases that combination can be rolled into. And we want to find those total number cases because we want to find the total number cases that we can possibly roll this sum of 9, and we want to put it over the total number of possible rolls that we could have. And then that will give us our probability. So our combination of 3, 3, 3, it's pretty obvious to see that there's only going to be one permutation that has a rule of 3, 3, 3. I mean, all three numbers are the same, and that's the only way you can have it. If we have 1, 4, 4, this is two numbers are the same, but one is different. There are going to be three permutations for this one because, you can think of each case as where this one different number is going to be. One case is going to be that it's in the first position. One case is going to be it's in the second position. One case it's going to be in the third position, and the rest of the positions are just going to be autofilled with 4s. And then, that's a valid descriptor of the entire combination. And there are only three ways to do that. So then the whole permutation of this combination will be 3. And then 2, 3, 4, number of permutations of this combination will be 6. We have three different things, and if we're finding its permutations, it's just going to be 3 factorial or 6. You can also think of it as, we have a group of 2, 3, 4, and then for the first number, we want to pick one of them. So we have 3 choices. That's going to be, 3 choices. And then the second one, we're going to have 2 numbers left, no matter what. We can't pick the same number again, so we'll have 2 choices for that. So far we have 3 times 2, and then the last space we have one number left, so that'll just be one choice. So then our number permutation for that will be 3 times 2 times 1, or just 6. So then our total number of permutations of dice rolls that we have to equal a sum of 9 will be 1 plus 3 plus 6, or 10. And then again, to find the probability of our dice rolls equaling 9, we're going to put this number of permutations over the total number of dice rolls that are possible. How many are possible? Well, we have 4 numbers that are possible on each die roll. If we roll it 3 times, then we're going to multiply this 4 3 times, or we can say that this is 4 cubed. So 4 cubed is just 64. So then our probability will be 10 over 64. We can simplify this to 5 over 32, and that will be our answer. If we look over here, that is your answer. Anything you want to say about that, Bill?
Yeah, like when you're dealing with like stuff that's saying like all but one, like here it's saying like the sum of all but the bottom square, all the visible ones, which is basically all but the bottom square. You normally are gonna be using taking like the stuff that's excluded and then just like 1 minus in that. So like here we see that the side on the bottom has to add up to 9. So like that.
Yeah, so if working with something is kind of difficult and you see that it's a case where you're getting all but one stuff, then you can try converting it into that just one working method, I guess. And in most cases it will be easier that way. So yeah. Okay, here's our last target problem, number 8. How many positive integers less than 2011 cannot be expressed as the difference of the squares of 2 positive integers? Okay, so this problem was kind of a wacky problem. we do have the results PDF, or actually it's not here, but wait, give me 1 second. I can send a link to it in the chat. Okay, yeah, so we do have the results PDF for this year. And then in Target, you can see that the first 5 problems are decently easy. A lot of people got it right. 6 problem was a little bit harder. 7 is all right. But then you can see that they only had 21 people answering it correctly, and all the other ones were like a lot higher. So I basically, oh whoops. Basically, 8 was a bit of a tough question. So if we're solving number 8 and you don't really understand or you feel like it's a wacky problem, that's probably all right because it probably is a pretty wacky problem. Um, so so yeah, just I don't know. I guess don't bog yourself down if you can't understand this problem. Also, um, I don't know, we thought about this problem for a little bit, and we could only find or like the solution that we found was a little bit weird. So maybe you guys can try finding like a different solution, and if you guys find one and it's like easier or better than ours, you guys can let us know and we could talk about that. But we're just going to show the solution that we found. Again, it might not be the best or intended solution, but regardless, this problem was a little bit wacky, so the solution either way is probably going to be a little bit on the hard side. But without further ado, we will just show our solution. So first, we're going to model the difference of squares of 2 positive integers. We can just say, let's just say the 2 positive integers are a and b. So we're looking at a squared minus b squared. We are going to model this as a plus b times a minus b, right? This is just the factoring of the difference of squares. So we're going to model it like this to see if we can find anything about like the properties of these factors, and like what they can essentially be multiplying to. Just working with the raw like a squared minus b squared, where each of them has to be, where a and b have to be integers, or positive integers. It's a little bit hard to work with, and like we couldn't think of anything that was I don't know, like intuitive to come up with this raw form. So we're gonna work with this a plus b times a minus b form. Now, what we're going to do here is we're going to look at cases of what our a minus b term will be equaling to. And we're going to start at the very lowest it can be, and we're going to work our way up. So we're going to start with case that a minus b is equal to 1. And let me just draw some lines here just to make it a little bit more neat. Okay, so let's first look at case where a minus b equals 1. Now case where a minus b equals 0, that really doesn't do anything. When our a minus b is equal to 0, then our sum is just always 0, and it's not even 0. It's talking about positive integers. So when a minus b is equal to 0, that's not going to do us any help, and we can't have a minus b is equal to any negative number, because that would mean that b is larger than a. If b is larger than a, then b squared is going to be larger than a squared, which means that a squared minus b squared is going to be a negative number, but we're only looking for when this difference is a positive number. So essentially a is always going to be greater than b. So the difference of a minus b is always going to be positive. So now we're going to start from our lowest case where a minus b is equal to 1, and we're going to work our way up. So a minus b equals 1. Now a and b have to be positive integers, but other than that, they can be anything. So let's start with the lowest case that we can have, with where a minus b is equal to 1. So let's have a row of a's here, and let's have a row of b's here. And again, a's had to be larger than b's. So our smallest case will be 2 and 1. A is equal to 2, b is equal to 1. If we go down to a is equal to 1, then b will have to equal to 0, but a and b both have to be positive integers. And then what is our next highest a and b case? Well, we can increase a and b by 1, and that's the smallest we can increase them by because they are integers. So our next smallest case will be a is equal to 3, b is equal to 2. And you can see that our cases will just go like this. We're adding 1 to each one. So essentially, these are our cases when our difference is 1, is equal to 1. Now, when a and b are equal to these numbers, what is our difference of a squared and b squared? Well, let's still use this formula on the right, because again, it can give more insights than just the raw a squared minus b squared. So if we're looking at this here, and we're looking at where case a minus b is equal to 1, then this term in this case will always equal 1, right? I mean, that's what we defined it to be. So a minus b is always going to equal 1. That means this difference is just going to equal a plus b, which means that, in all these cases, our difference is just going to be the sum of a and b. So in our first case here, we can see that our difference is going to be 3. And then in our case here, we can see that our difference is going to be 5. And here it's going to be 7, and here it's going to be 9. We can see that all of these sums of these two numbers are increasing by 2, right? Because, I mean that makes sense, right? Because from each of these steps, we're increasing each of a and b by 1. So we're going to increase the total sum by 2 every time. Now, what is this telling us? This is telling us that it's possible to represent 3, 5, 7, and so on as a difference of two positive integer squares, right? And again, we just said that these terms were increasing by 2 by each step, right? Which means that all of the odd numbers starting with 3 are going to all be covered. So that's a step, right? We're getting some more information about what's going to be covered by this and what's not going to be. So, and we can see that that's all it's going to be, right? It's just going to continue on like that forever. So for this case, I'm going to write all odd numbers are covered. And I say are covered, it's just I just mean like can be written as this. So all our odd numbers are covered except for one. Except for one, like the positive integer 1. Okay. So that's a step. Now let's try to look at higher differences and see if we can get any more information about this problem. So let's look at a case where the difference a minus b is equal to 2. Let's again list out our a and b rows, and let's start from when they are the smallest. So a is equal to 3 and b is equal to 1. And we're also going to gradually increase this. And so this will be 4 and 2, and then this will be 5 and 3, and this will be 6 and 4, and this will go on. like that. Now, the case where a minus b is equal to 2, the difference, or this product right here, now this term is always going to be equal to 2. And then so whatever the sum of a and b is times 2, that's going to be what our final term is, what our difference of the squares are. So let's just find what they directly are right now and see if we can find a pattern after we've listed them out. So we can see that this sum is going to be equal to 4. You multiply that by 2, that's 8. The sum is going to be 6. We multiply that by 2, that's going to be 12. The sum is 8. We multiply by 2, that's 16. The sum is 20. We multiply by 2, or sorry, this sum is 10. We multiply by 2, and then it is 20. We can see a pattern in our products in that they are differing by 4. We can see that this makes sense because, we're multiplying our sum by our difference, right, which is a constant 2, and our sums between each of these pairs of terms are increasing by 2, right, just like last time. By each consecutive pair of terms, we're increasing b by 1 and we're increasing a by 1, which means that we're increasing the total sum by 2. So if we're increasing the total sum by 2, and then we're going to multiply that by the difference, which is a constant 2, that means the total product will be added by an additional 4 every time we go up a pair of consecutive terms. Or every time we go up a consecutive pair of terms, my bad. Okay, now what is this going to mean? Well, we can see that 8 is 0 mod 4, right? 0 mod 4 just meaning that it is divisible by 4. If 8 is 0 mod 4 and we're always increasing the sequence by 4, that means all of our 0 mod 4 numbers, all of the numbers that are divisible by 4, except for 4, are going to be covered, which means that they can't be expressed as a difference of squares of two positive numbers. So again, this is making some progress. We're getting some more information about the scenario. So I will write this. I will write this in our case box here. I would say that all 0 mod 4 numbers are covered except for the number 4. Okay, so again, that's making some progress. Right now, we don't really know where this is ever going to end, but hopefully, sometime we will find like an end to this. Now, by now you might be able to see that this problem might take a little bit longer than is necessary. So, and it is a little bit harder than usual. So, maybe instead of working on this problem, you can try to work on the other problem if you haven't already. Because that problem was easier. But if you do have like the time and you thought the other problem you're pretty confident in, then you can like just continue to work on this problem, I guess. But yeah, it is your choice on your test. So yeah. Okay. So now let's look at the case where the difference is equal to 3. Okay, so again, we're going to make our rows of A and B. The smallest pair is going to be 4 and 1, and then the next smallest pair is going to be 5 and 2, and then we're just going to continually increase this. So 7 and 4, and then it's going to go, so on. So now our A minus B term is going to be a constant 3. And our product is just going to be a constant 3 times what our sum is. So again, let's try finding this out for some number of terms and seeing if we can find a pattern for it. So for 1, our sum is 5, multiply that by 3, that gives us 15. 5 and 2, our sum is 7. Multiply that by 3, that gives us 21. 6 and 3, our sum is 9. Multiply that by 3, that gives us 27. 7, 4, that gives us, the sum is 11, and multiply that by 3, and we get 33. Here we can see that the that the differences between our sorry, the difference sorry, here we can see that the difference between our difference of squares of two consecutive pairs of numbers is 6. Now this makes sense because between each of these pairs of numbers, we are increasing a by 1 and we are increasing b by 1, which means that we are increasing the total sum by 2, which means that we are increasing the total product, which is going to be multiplied by 3, by 2 times 3, which is 6. So now, you should be able to see that we are always going to, this difference between our, difference of squares of consecutive pairs of numbers, you can see that this number is always going to equal our difference, a minus b, times 2. This will come in useful later, so remember that. But yeah, so this case our difference is going to be 6. Now, because we started on an odd term, 15 as the difference of our squares, and we're increasing this by a constant even number of 6, this is always going to hit an odd number every time, right? Now, in our case where our difference was equal to 1, we said that all odd numbers are covered except for 1. So if we're still hitting odd numbers, this is not going to change anything. We're still hitting numbers that we said were covered before. So this case does not add anything new. So yeah, this case does not add anything new. I will not write anything for it. Now let's look at our case of a minus b equals 4. Let's write out our a and b's. So 5, 1, 6, 2, 7, 3, and so on. Our initial difference term is going to be the sum times the difference. The sum is 6, the difference is 4. It's going to equal 24. Now, we said that this difference was always going to be equal to 2 times our difference. Here, the difference is 4, so this difference is always going to be equal to 8. So our next term is always going to be equal, or is going to be equal to 32, and then this term is going to be equal to 40, and so on. Now, one thing you can see about this case is that 24 is 0 mod 4. 8 is also 0 mod 4. So if we're always adding 0 mod 4 to a 0 mod 4 number, what does that mean? We're always going to get a 0 mod 4 number. So, if we're always hitting 0 mod 4 numbers, and in our case where our difference is equal to 2, we saw that all 0 mod 4 numbers are covered except for 4, then again, we're not hitting any new numbers. We're not covering any new numbers that we didn't know we were already covering before. So again, this case does not add anything new. Okay. Let's look at our case where a minus b is equal to 5. Let's just list out like our first two, a and b. It's just going to be 6 and 1, 7 and 2. This first term is going to be 7. Our sum of 6 and 1 times 5, which is 35. The difference between the terms is going to be 2 times our difference, which is 2 times 5, which is 10. So our next term is going to be 45. So we're going to plus 10. And we're going to keep on adding 10, right? Now, what do we see here? We see that our starting term is odd. We see that our difference is even, which means, again, like our difference, where our a minus b is equal to 3 case, again, this is only going to hit odd numbers. So again, this is not going to add anything new. Our first case said that all odd numbers except for 1 was covered. Now, maybe you're starting to see a pattern here and you're a little bit suspicious. You know, if I could prove that this number will always be odd and this number will always be even, then I could always say that um, this is not going to add anything new, right? Um, because we said that the odd numbers were already covered. But this where this is odd and where this is even, this only seems to happen when our difference is equal to an odd number, right? When our difference was equal to 4, an even number, this was even. So then this is not going to work. So maybe let's try proving this only when our case of difference is equal to an odd number. So again, if we can say that when our difference of a and b is equal to an odd number, if we can say that that will make this number always odd and this number always even, then we can say for all of our odd difference cases, it's not going to add any new numbers, which means that we can disregard all of them. Obviously, if we can disregard all of our difference equals odd cases, then that would be really nice. So let's try to see if that will work. Well, this difference right here, what did we say this was before? We said that this was 2 times the difference. That is our case, right? Now our case is always going to be a positive integer, and if we're multiplying by 2, then it's always going to be an even number, right? So then easily we can prove that this difference is always going to be even. Now what about this number always being odd? Well, um, what is this number going to be? This number is going to be a plus b times a minus b, right? But we're going to take the a plus b and a minus b to be the first term that we list here. Now, you can see that in an odd number case where a minus b is equal to an odd number, this is always going to be odd. That's very easy to see. But what about a plus b? Well, you can see that a plus b will always have to be odd as well. If I ever have a difference of 2 numbers being odd, then the sum of the 2 numbers will have to be odd as well, right? I mean, you can just think of this using parities, right? Like, what are the ways where I can have a difference of 2 numbers being odd? Well, I can either have an even minus an odd number, that will give me an odd number, or an odd minus even number, that will also give me an odd number. But if I have an even number minus the even number, or an odd number minus an odd number, these will equal even numbers, right? So like this. So we see that, our 2 numbers will always have to be, 1 is even and 1 is odd. Now, what does this say about the sum of the 2 numbers? Well, the sum of the 2 numbers is then always going to be odd, right? We're always adding 1 odd number, 1 even number. So the sum of them is also always going to be odd. Now, what is this saying now? This is now saying that the product of these 2 numbers is always going to be odd times odd, which is always going to be an odd number, which means that the starting number is always going to be an odd number. And we just said that this number is always going to be an even number. So then we can say that, in a case where a difference is odd, then we're always going to only hit odd numbers. So then we can finally say that we can disregard all of our odd cases, or all of our cases where our difference is odd, and now we don't have to look at them anymore. Okay, so that's nice. So now maybe let's look at our even cases, and maybe we can see we can try to like eliminate all of them like how we did with the odd cases, or maybe find another pattern and it just tells us something about all of our even cases. So let's look at our next even case and see if we can find any information about it. So case where our difference a minus b is equal to 6. Let's just list out the first few terms. A is 7, b is 1, a is 8, b is 2. Our sum here is going to be 8, so then our product is going to be 8 times 6, or 48. The difference between our 2 terms is going to be 2 times our difference, which is 6. So this our difference is going to be 12. So then this number is going to be 60. We're always going to be adding by 12. Now, what do we see here again? Just like our a minus b is equal to 4 case. Again, we see that our difference between our two numbers is 0 mod 4. And our starting number is also 0 mod 4. So again, if we start with a 0 mod 4 number and we're always adding a 0 mod 4 number, we're always going to hit 0 mod 4 numbers. And from our initial difference equals 2 case, we already said all the 0 mod 4 numbers are covered except for 4. Then if we keep on having this, then this is just redundant, right? So maybe we're having suspicions that when our difference is equal to an even number, then this is always going to happen, and then we can always disregard it, right? So if that were the case, that would be good, because that would mean we can disregard all of our differences equal to even number cases. So let's try to prove that that is actually correct, and then we can roll with that, right? So again, we are trying to prove that our starting number in difference is equal to an even number case is always going to be divisible by 4, and so will be the difference between, the difference of squares of two consecutive pairs of terms. So again, we said that our difference between these terms are going to be 2 times our difference. Well, if we're only looking at even cases, then each of these, if we're only looking at cases where our difference a minus b is equal to an even number, then obviously, with the definition of even, that a minus b term is always going to have at least one factor of 2. So then if we're doing 2 times that a minus b, which always has at least one factor of 2, then the 2 times a minus b term will always have at least 2 factors of 2. If something at least has 2 factors of 2, what does that mean? That means it will always be divided by 4. And that is what describes this term. So now we can see that this will always be divided by 4. But what about this term? Well, this term, again, this term will be a plus b times a minus b with our initial a and b numbers. Now, we like we said before, this a minus b term will always have at least one factor 2. If we can say that a plus b will also always have one factor 2, then we can prove that this will always be divisible by 4. Well, we can think about parities again in this case. If we have two numbers, two integers, and they subtract to an even number, that means they have to be either even and even or odd and odd. What does that say about their sum? Well, even and even summing will always be an even number. Odd and odd summing will always be an odd number. Will always be an even number. So in both cases, it will always be an even number, which means what? Which means if we have a case where the difference of these two numbers is even, then the sum of the two numbers will also be even. Now, if a number is even, what does that mean? It means that it also has to have at least one factor 2. So both these terms has at least one factor 2. That means the product of this will always have at least two factors of 2, which means that each of these terms will always have to have 2 factors 2, which means each of the terms will always have to be 0 mod 4 or divisible by 4. So that's great, right? We just said that with all of our even cases, all of these terms are going to be divisible by 4, which means that they're going to be covered by our previous difference equals 2 case already, which means we can disregard all of our difference is equal to an even number case. Now, this is great, right? We just said we could disregard all of our difference is equal to odd cases except for our first one, and we could disregard all of our difference equals even cases except for our first even case. So that means we can disregard all of our cases except for our first two cases. So now we can just look at our first two cases and we can find what numbers will satisfy this condition. And we can see what we wrote down. The numbers that are going to can be expressed as difference of squares will be all odd numbers except for 1, and all numbers divisible by 4 except for 4. So now we had to count what numbers less than 2011 that are positive integers cannot be expressed as as a difference of squares of two positive integers. So we had to find the positive integers less than 2011, which are not described by these two statements. So what is that going to be? Well, the complement of the set of all odd numbers except for 1, that's going to be all even numbers, 2, 4, 6, 8, etc., but also with 1. So because this set does not have 1, so the complement of it has to have 1. Now this is all divisible by 4 numbers except for 4. So the complement of this set is going to be all numbers that are not divisible by 4. So 1, 2, 3, 5, 6, 7, 9, 10, 11, and so on. But this does not have 4, so the complement of it is going to have 4. Okay. Now, for a number to be satisfied, for a number to be in this condition, it has to be in both of these sets. Why? Because this set says that if a number is in this set, it will be covered. If the number is in this set, this also says it will be covered. So if a number is in this set, then it's going to be covered. So it can be expressed. So it cannot be expressed. So basically, if a number is in this set, then it will not satisfy the condition that is given in the problem. Likewise, if a number is in this set, it will not satisfy the condition that is given in the problem. So if a number is in either or of these, then it's not going to satisfy the condition that is stated in the problem. Which means that we want a number that is not in both these sets. Which means that you want a number that is in both of the complement of each of these sets. So what is in the complement, or what is in the complement of both these sets? Or wait, what is both in the complement of both of these sets? Well, we can see that's going to be 1, 2, 4, 6. It's not going to be 8. So start 10, 12. So it is going to be 10, but it's not going to be 12 because 12 is not, or it is a multiple of 4, so it's not going to be in here. But if we go to 14, 14 is going to work because 14 is not divisible by 4, so it's going to be in here. So, but it's in here as well. Okay, so what can we see here? Well, in both these sets, they're both going to have, except for 1 and 4, it's going to have every 2 mod 4 term. And this also makes sense because if we're just looking at all odd numbers and all 0 mod 4 numbers, if we're just looking at that and we want a number to not be in both of these, then it has to be 2 mod 4, right? Because it had to be even from this, but even numbers are either 0 mod 4 or 2 mod 4. So because it can't be 0 mod 4, then it has to be always 2 mod 4. Now, we have 1 and 4 in here because this says all odd numbers are covered except for 1. So 1 is not covered, and 1 is also not divisible by 4. So 1 is not covered in both of these. So then it is not covered, which means it cannot be expressed. So So we will count 1. And we also will count 4 because, it is not in this set, and it is also not in this set because it's not an odd number. But otherwise, all of our other numbers will just be 2 mod 4 numbers. So all 2 mod 4 numbers will be in here, and all of the numbers that are in here will be 2 mod 4. So now we just need to count this set of numbers. We need to count how many numbers are in the set that are also less than 2011. Well, 2010. Well, so basically, all positive integers less than 2011 will be the numbers of 1 through 2010 inclusive. 2010 divided by 2 is 1005, and 1005 is an even number, which means that, or sorry, it's an odd number, which means that 2010 will be 2 mod 4. So 2010 will be in the set. But how many 2 mod 4 numbers are going to be in between 1 and 2010? Well, what we can do here, counting 2 mod 4 numbers might be a little bit weird. So what we can do instead of counting 2 mod 4 numbers is we can count all even numbers between 1 and 2010 and divide that number by 2 to find the number 2 mod 4 numbers. But so why can we do that? Well, it's because all even numbers are either 0 mod 4 and 2 mod 4. And yeah, so if you get a number of even if you get a number of even numbers, you can divide by 2 to find the number of 2 mod 4 numbers. But you have to be still careful here. Like, what do you have to be careful about? Well, let's say you have a set of even numbers: 2, 4, 6, 8, 10, 12. And like I was saying, you're counting the number of even numbers, you're dividing that by 2 to get the number of 2 mod 4 numbers. So you can see that if we just take this set, we have six even numbers. We divide that by 6, we get 3, and we can see that there are, in fact, 3 2 mod 4 numbers: 2, 6, and 10. But this only works because we took pairs, like we took alternating pairs of 2 and 0 mod 4 numbers, right? This is 0 mod 4, this is 2 mod, or sorry, this is 2 mod 4, this is 0 mod 4, this is 2 mod 4, this is 0 mod 4, and so on, right? So we have to do that. We can't interrupt a pair. If we interrupt a pair, then we're not finishing this pair, and then we can't divide it by 2. You can also see that we would count an odd number of numbers, and then we also can't divide that by 2. So basically what I'm saying is, we have to finish each of these pairs, and basically we just have to be worried about the last pair. These starting pairs will always be counted, but we just have to be worried of the last pair. How do we know if we've finished the last pair or not? Well, the last number of the last pair will always be 0 mod 4, right? I mean, you can just look at the pairs and how I've grouped it. The last numbers are always 0 mod 4, which means that we have to stop our counting on a 0 mod 4 number in order for this method to work. So we're going to look at a 0 mod 4 number in here, in this set somewhere. We want it to be close to 2010. From this number, we're going to count the number of even numbers that are here and below. Then we're going to divide that number of even numbers by 2. And that will give us the number of 2 mod 4 numbers between this and 1. What number are we going to use? Well, we can't use 2010 because this is 2 mod 4. So let's use the number that is 2 below it, 2008, because that is a 2 mod 4 number, or sorry, a 0 mod 4 number. So how many even numbers are at 2008 or below it? Well, 2008 is 1004 times 2. 2 is 1 times 2. And all of the even numbers are differing by 2. Um, so essentially, all of the even numbers can be counted as 1 times 2, 2 times 2, 3 times 2, and so on, right? And we're going all the way to 1004 times 2. So you can see that we can count the number of even numbers that are here just by counting what this number is, right? If we stopped on this one, we can see that we would count three even numbers, and that is correct. Okay, so what are we saying here? We're saying that there are 1004 even numbers that are at 2008 or below. And then, like I said, we're going to divide this number by 2 to get our number of 2 mod 4 numbers that are at 2008 or below. And this is going to equal 502. Now, the numbers that we didn't count that are also in this set are 2009 and 2010. 2009 is not a 2 mod 4 number, but 2010 is. So then we want to add 502 by 1. So then we have 503. Now, are we done finally? Well, no, because we only counted the 2 mod 4 numbers in this set. But like I said before, we had 2 extra numbers in the set that were not 2 mod 4, which is 1 and 4. So we had to remember to count those as well. So now we just have to add 2 for each of those 2 numbers, 1 and 4. There are in our set that we did not count as 2 mod 4 numbers, and then that will bring our total to 505. And we can see that the answer is 505. All right, but that was a very lengthy solution.
That was quite the experience.
Yes. Well, how long was that? Like
25
45,
minutes-ish.
20?
Yeah.
I sent the link. Oh, wait. No, I sent the link at 57. So it's like 40 minutes-ish.
Oh, you sent the. Oh, wow. Okay, so if you see this, don't do that.
Well, I mean, so like Target, you do 2 problems at a time, right? So I mean, like if you feel confident about 7, then you can do it. This might not be the most ideal solution, so maybe you guys could have found a better solution and done it quickly. But yeah, this is a difficult problem to do with an average time of 3 minutes. Um, is there anything you want to say for this problem, Bill?
This problem's kind of crazy.
Well, our solution is crazy. Maybe
Yes,
the
our
problem
solution
actually
is
is
crazy.
not crazy,
There's
but we
very
couldn't
well a
find the
chance that
best
there's
solution.
not a crazy solution.
Yes.
Um,
Okay. Um,
I
if
don't
you don't
really
have
have
anything else
anything
to
to say.
say,
Just like,
do you want to switch over now?
yeah, sure. What do you mean by switching over? Like, do you want me to do it?
Yeah, if you want to.
Yeah, that's fine. Okay.
Okay, I'll stop presenting. Are you saying anything? I don't think we can hear you, by the way, if you're saying something.
Oh, sorry. My bad. A triangle has three sides of integer length. What is the product of the smallest and largest possible values for the length of the unknown side if two of the sides measure 13 and 16 units? So, um, I mean, just like, what is it called? It's, what's that
What?
rule called?
Wait, there's a name for that rule?
I think. Well, anyway, it's like, I mean, it's pretty easy. I think everyone should know this. It's where, if you know, like,
Oh, side.
two sides of a triangle, if you add them up, has to be greater than the third side. So,
It's called a triangle inequality theorem.
okay, cool. Triangle inequality theorem. Basically, yeah, the third side has to be less than the sum of the two, and from the sum of the two other sides, and also, and in turn from that, we can also get that it has to be greater than the difference of the two other sides. So so it has to be greater than 16 minus 13, so greater than 3 and less than
Or
29.
like you can see that if you like draw a triangle and try to get like the largest or smallest length. Like,
Right.
do you want to show that?
Yeah, sure. So like say we have a triangle like this. Like the largest length in theory would just be like the large if we keep these two constant,
Like,
the largest length for the third side will be like if we stretch these two sides like as flat as possible. So like essentially like a flat line. Like this will be
yeah,
like
we want it to be as wide as possible,
as wide as
which
possible.
would
So this is
be
like the longest.
flattening out
Yeah,
the triangle into a line.
right.
And then
And
the
for the
length of the
shortest,
line
you'll
would
be
be
like
like,
making it as narrow as possible. So ideally, it'll just be like a line. Like here's the point, and then the third point will just be like here, like this, and that will be the shortest. And so yeah, like that we'll get it'll be greater than 3, less than 29. So because they're integers, it'll be 4 to 28. So that's 25. Oh, my bad. That's not what the question was asking for. So the smallest is 4, the largest is 28. So 4 times 28, you get a calculator for this, and it comes out to 112. And yep, 112. Okay, number 2. A bicycle which normally sells for $215 is on sale today at 30% off. And another bicycle which normally sells for $260 is on sale today for at 50% off.
Ishan, you missed the really wacky problem.
Bishan, you missed the problem Austin spent 40 minutes on.
Yeah, but it's okay. You can watch it later. It was really weird. But yeah.
If the Shulai family purchases both bicycles today, what percentage of the original price will they pay? So, I mean, we can just like find out how much they paid. 215 times 0.7 plus 260 times 0.5, and that'll get you 275.5, and then you just put that over the original price, which is will be 215 plus 260, that's 475, and you get 58%. So 58%. That's pretty easy.
Did you run it correctly?
There was no rounding.
Wait, what?
There's no rounding. It's all exact. It all comes out
No,
exactly to that.
no, your last ratio fraction.
That's also not rounded.
You should calculate the top thing
Oh, sorry.
again.
I think I put it in the
Try.
calculator wrong. My bad.
Uh,
I put it in the calculator wrong. 280.5.
280.
And now this should give us. Oh, now it's rounded. So, but this rounds to 59%.
Was that not rounded before?
What?
This is really nice, I guess.
275.5. Yeah, it wasn't rounded before. I wasn't expecting that. Okay, number 3. If x and y are positive integers such that 5x plus 3y equals 100, what is the greatest possible value of x, y? So, typically, when you have something like x plus y equals something, x plus y, typically we have x plus y equals something, and then you're looking for the greatest value of xy, you typically want x and y to be like as close as possible. But in this case, we have 5x plus 3y equals 100. So when you have something like this, um, I actually don't really have like a reason for it. Austin, do you have a reason for like why the ratio should be what it is?
Um, I'm not sure, like, or I guess, um, so like, so with 5x plus 3y equals 100, you can say like y is equal to 100 minus 5x over 3, right?
Right, yes.
Or do you want to write that down?
Okay. Uh,
Uh,
wait. Did I
uh,
write it down wrong?
yeah, y should be equal to 100 minus
Oh,
5x over 3.
I misunderstood what you said. Y equals. Yeah.
Or
Oh,
all of it is over 3.
yeah. Don't mind me. Okay, all of it over 3.
Okay. Um, now, now you can substitute y as that, right? So then your product is like a quadratic in x, and you want that to be maximized, right?
Yeah.
Uh, wait.
Mhm.
Uh, wait, I'm kind of confused.
Okay. Well,
Uh,
I mean, we can just go like the original way. So, okay.
I
So, if
mean, like in essence, it's
mhm.
like you, it's like you want to decrease 5x plus 3y as much as possible. Like decrease it so that your x and y can be larger, kind of. Um, and then but also having them like close together as you want like because you know if you have two numbers that are closer together it's going to give a higher product than if they're farther away or that and they sum to a constant but I don't know it's kind of weird I guess okay.
Okay. I mean, maybe you can also like explain it with like if you square this, like say like so that's gives you 25x squared, 9y squared. I mean, maximize x, y, you want to minimize like these two parts, right? You want to minimize these two.
So like I think my thing would work, but it doesn't give the answer that we thought it would give. But I think mine it would actually be right. And you know, our initial suggestion was not right. Like so you can say
Hmm.
y is equal to 100 over 100 minus
Yeah,
5x over 3, right?
yeah.
Then the product is 100 thirds x minus 5 thirds x squared, right?
Um, 100 thirds x minus 5x squared thirds.
Yeah, and
Yeah,
then I mean you're trying to maximize this, and this is just a quadratic in x, right? You can choose
yes,
whatever you want x to be.
yeah,
When you're maximizing a quadratic function, and you know, this case you have a negative a, right? So
right. There is maximum.
the maximum would be at the vertex, whereas the
Yes,
vertex, well, it's going to be b over 2a, right?
yeah,
So then it's going to be, um, or x equals negative b over 2a. So then x is going to equal negative 100 thirds over 2 times negative 5 thirds, which is equal to 100 thirds over 10 thirds, which is then equal to 10.
right.
So from this, we would find that x is maximized when x is equal to 10. But
But
I mean,
y has to be an integer,
yeah,
right?
but y has to be an integer.
Right.
So, but it will also not give, see, but in that case, y would be equal to 50 thirds, right? And
Hmm.
then the ratio of y over x is, oh wait, no, it does give the ratio. Wait, it does give the ratio
It
that
does
y
give
over
the
x is 5
ratio,
times. Okay, I guess our thing was right then. I just did not. Okay.
but why is it right?
It's like, I guess it's a little bit non-intuitive, but to explain it as intuitive as possible, there's a certain ratio that, you know, you want x and y to be in so that
To maximize the x, y.
like to minimize their sum yet to
Right.
maximize their product.
Yeah. And in this
Okay.
case, the
I mean, you don't have to exactly know that here. This problem would it's just much simpler. You
right.
don't
I mean,
have
you
to
could
know
just like
all of it.
try some numbers. It's not that many.
I mean, generally, you just need to know that, you know, if you're finding product of x and y, you just generally want x and y to be as close as possible.
Right. And in this case, if they're like this, you want y to be what x multiplied by and x to be what y is multiplied by. So like x to y should be in a ratio of 3 to 5. But I guess you just like keep go where we were. So if we look at the question, 5x plus 3 times something equals 100. So y has to be divisible by 5. Y has to be 0 mod 5. Because 5x is definitely going to be divisible by 5. So for 3y to be divisible, for them to add up to 100, 3y would also have to be divisible by 5. So that like limits how big our y can be by like a lot. So so now let's think about like this ratio thing, 3 to 5. So for them to add up to 100 and for the ratio to be 3 to 5, it would kind of be like, so let's just take a random guess. If y equaled 15, x is going to have to be equal what? 9. And this gives us 90. So if we plug this into this left side, it'll give us 90. And if we go up, y equals 20. x would have to equal 12. This gives us what, 60, and that's 120. So this is closer to 100, and like y, we can't really modify y. Y always has to be a multiple of 5, so we add 2 to x, so we end up with just x equals 11, y equals 15, because this is the closest to the 3 to 5 ratio. Um, yeah, and then if we do x times y equals 165. We can also try y equals 20 and x equals 12. We have to modify 12. So it will be y equals 20 and x equals 8. And I mean, we can pretty obviously see that this is further away from 3 to 5 than the other one. But actually, it's not further, is it? Yeah, no, it is further. Never mind. It is further from 3 to 5 than 11, 5. So, and if we change this, multiply these two, we get 160, which is less than 165. The greatest possible value of xy is 165. Okay, so
Also, yeah, for this part, you didn't necessarily have to know the ratio, like, 3/5. You could just like the big thing to know so that you don't test a lot of cases is that y is 0.5.
yeah, y is
And then
0.5. That's kind of,
you really just have to, like, you can test a random value and then test some more random values, see what direction you have to go, and then just keep on testing until like you reach a high point. But I mean, that's really not going to take very long because one, you have a calculator, and two, you're just looking at y is divisible by 5 cases. So yeah. But also, like, if you know the ratio, that helps a bit. Yeah.
okay. It's 7:59, by the way. You want to keep going, or
Um, up to you.
uh what do you think? I don't really care.
I mean, if you want to keep going, you keep going. If you want to stop, we can just stop.
Let's stop.
Okay.
Okay.
All right. Well, thank you for coming to our math counts meeting. So we will start from number 4 team next week. We're still on 2011 nationals. So after we finish 2011 nationals, we will likely move on to 2010 nationals. Unless if one of you guys does not want to do 2010 nationals and would rather do something else, you can let us know and we can do that instead probably. Um, but yeah, for now that's it. See you guys next week. Goodbye.